Great. Good afternoon, everyone. My name is Lalith Talagala. I work in the NIH MRI research facility. That's the scanner that we manage as NMRF 3T scanner, and it's one of the Siemens Kairos we have in the NMR center. So today's lecture is about perfusion imaging. So we will discuss the techniques that we normally use to sensitize MR images to blood flow. So here's the outline. And my goal in this talk is to give you an overview of the techniques and the steps involved in doing blood flow imaging with MRI. And we won't go into the detail of each one of the steps or talk about the latest research, but we will cover most of the basic aspects in perfusion imaging. So we will cover two main methods. That's one is the dynamic susceptibility contrast technique and the arterial spin labeling technique. And in each case, we will talk about the method and how we quantify the signal changes. And also in ASL, we will talk about the popular labeling techniques. And at the end of the talk, I will touch upon some functional imaging using blood flow. So just to make sure that we are all talking about, thinking about the same thing, like perfusion, we refer to capillary blood flow. And here we would like to measure the following parameters generally: blood flow itself, blood volume, and the mean transit time. And the blood flow is normally measured as a quantity of blood per unit time per some amount of tissue, and blood volume is the quantity of blood in a certain amount of tissue. And the mean transit time is the average time the blood spends on traversing the capillary bed, and which is measured in seconds. So the normal values for the brain, and we will in this talk concentrate on the brain. So we will be talking about cerebral blood flow. So CBF in the brain is roughly, in the gray matter, is about 60 to 80 milliliters per minute per 100 grams. And in white matter is about 20 to 30 milliliters per minute per 100 grams. Cerebral blood volume in gray matter is about 4 to 6%, and the white matter is about a factor of 2 less. And the mean transit times are around 4 to 5 seconds in gray matter and a little bit longer in white matter. Just some numbers to keep in mind. So as I mentioned, there are two main techniques to do perfusion MRI these days. This is just a quick comparison of the two techniques. In the dynamic susceptibility contrast technique, we use external contrast agents like gadolinium. So therefore, this requires a contrast injection. And this method produces large signal changes, and therefore we do not have to average the signal for too long. So therefore, this method is quite fast. And because we have to administer external contrast agent, this method is generally restricted to a single application, and therefore is more suitable in a clinical setting. On the other hand, the arterial spin labeling, we do not need to inject an external contrast agent. We use blood itself as a tracer. But this method produces signal changes that are quite small, and therefore we have to average for a while. And so this technique takes about at least about 5 minutes on the average to get decent signal. But because we do not have to administer any external contrast agent, we can do this experiment multiple times in a single sitting, and therefore it can be used in a clinical setting as well as in research studies. So let's look at the dynamic susceptibility contrast technique a little bit more closer. And here what we do is we monitor the passage of gadolinium through the tissue with some kind of a rapid imaging technique. So we inject the contrast agent as a bolus in the arm, and the contrast agent is then carried by blood to the heart and then throughout the body. And when the contrast agent is is traveling through the brain, we actually acquire images through the brain, and using typically gradient echo EPI techniques, echoplanar imaging. And in this case, we use a TR about 1.5 to 2 seconds, and we acquire these images over and over again so we can monitor the passage of contrast through the brain. And the whole experiment lasts for about 1.5 minutes. And in this case, we use a TE around 30 to 50 milliseconds, depending on the field strength, because we want to weight these images to T2 star, just like in bold, so that we can actually we will be able to observe a signal change due to gadolinium, presence of gadolinium. So how does this technique work? So here we have two situations. A situation where the blood within a voxel without gadolinium, and where the another condition is where the blood within the voxel is filled with gadolinium. So gadolinium is a paramagnetic agent, and also it stays intravascular. So therefore, when the gadolinium is present in the voxel, you will have a difference in magnetic susceptibility between tissue and blood. So the magnetic susceptibility difference increases when the gadolinium is present in the voxel. And this leads to increased field homogeneity within the voxel. That results in decrease in T2 star or increase in T2 star relaxation rate. And when we, under these conditions, when we use a gradient echo or spin echo MRI signal, we will be able to see reduction in signal, because shorter T2 star means reduced signal in a gradient echo MRI image. So here's an example of series of images acquired while the gadolinium is passing through the brain. And in these images are echoplanar images acquired at a TR of 2 seconds. So these are the same slides acquired over and over again at a repetition rate of 2 seconds. So at the beginning, we see a baseline signal, high signal intensity throughout the brain. As the contrast agent starts to wash in to this slice, we see a reduction in signal intensity, and at some point we see a peak signal loss. And as the contrast agent washes out from the slice, we see the signal intensity returning back to normal. And so these images were acquired with a T of 50 milliseconds and were taken at 1.5 T. So if you want to study what happens to the signal intensity more closely, what we can do is to extract the signal intensity from a single pixel across all the time points and look at the signal intensity time curve from any one of these voxels. Here I have extracted the signal intensity from two different voxels. One is a gray matter pixel, and another one is a blood pixel, where the signal intensity is mostly blood. So here we can see in both pixels the baseline signal is quite high. As the contrast starts to come in, the signal intensity decreases in both cases, and there is a peak signal intensity loss. As the contrast washes out, we see the signal intensity coming back. So this signal intensity loss that we see initially is due to the first pass of the bolus through this particular slice. And after the first pass, we sometimes see the recirculation of the contrast agent. That means the contrast agent is washing out and then comes back again for the second time, and creates a smaller signal loss, much smaller signal loss compared to the first pass. So here we see that the signal intensity loss in the gray matter is much smaller compared to the signal intensity loss in the blood pixel, and that is due to the fact that the concentration of the contrast agent in blood is much higher than the contrast agent concentration in tissue. So the signal loss gives you some information about the contrast agent of gadolinium present in the tissue at any particular time point. So what you would like to do is to convert this signal loss to concentration. So we know that from initial work on contrast agent work, we know that in the first order, the change in the relaxation rate due to gadolinium is proportional to the concentration of gadolinium. And we can also write the signal intensity in the presence of gadolinium as a function of the change in relaxation rate. And combining these two equations, we can actually find the concentration of gadolinium at any particular time as the negative logarithm of the ratio of the signal intensity in the presence of gadolinium over the baseline signal intensity. So now we have an equation where we can convert the signal losses into concentration estimates. So we can do that on a pixel by pixel basis for all the time points. Here's the signal intensity time curve that we saw in the beginning. Using this equation, we can convert that into a concentration versus time curves. And here we see that the blood has higher concentration of gadolinium compared to the concentration of gadolinium in tissue. So what we have is two pieces of information. We have concentration time curves in the blood, and we have the concentration time curves in the tissue. What we would like to do is to use these two pieces of information and try to obtain estimates of the parameters that we talked about in the first slide. That's the cerebral blood volume, blood flow, and mean transit time. So the concentration of in the arteries is generally referred to as the arterial input function, and the concentration time curve in the tissue is called the tissue response function. And these two can be combined using the tracer kinetic theory to come up with the estimates of the parameters that we need. And now this is a theory that has been established for a long time in the 1950s and early 60s for for use of radioactive traces, and we can apply the same theory in this case. And if you do that, you see that the calculation of CBV or estimate of the CBV can be obtained by the integral of the tissue concentration curve divided by the integral of the arterial concentration curve. So the CBV is simply the area under the curve of the tissue concentration curve divided by the area under the curve of the arterial time curve. So that is quite straightforward. But it turns out the calculation of CVF and mean transit time is a little bit more involved. And the same theory, according to this tracer kinetic theory, we can show that the tissue concentration curve is actually a convolution between the arterial input function as well as a second function that we refer to as the residue function. And this residue function is a characteristic of the tissue that we are observing. So in this case, we have we know the tissue concentration curve, we know the arterial input function, and therefore we can obtain this residue function by deconvolving the arterial input function from the tissue concentration curve. So after deconvolution, what you get is the scale residue function, which is scaled according to the cerebral blood flow. So the CBF can be estimated as the amplitude of the function that we obtained following deconvolution. And we know that the CBV was estimated in the previous slide. So we know that mean transit time is the ratio of CBV to CBF. So now we have a framework to calculate all three parameters of interest. So we can actually use that framework to calculate do the calculation of for each individual pixel, and then we come up with the CBV and CBF and MTT maps. And here are the maps that you get from the data set that I showed you a few slides ago. So in here we can see that the cerebral blood volume and cerebral blood flow in the right hemisphere is elevated compared to the left hemisphere, and also the mean transit time is reduced in the right hemisphere compared to the left hemisphere. That means the blood is traveling faster through the capillaries in the right hemisphere compared to the left hemisphere. These images are in the radiological coordinate. That's why I'm interchanging right and left. So as I mentioned, because we are using a TR of 1.5 to 2 seconds, we get actually information from all the slices through the brain. So you could do that for all the calculate the maps for all the slices. Here are a few slices in this particular example. In this case, we can see the full extent of the area of abnormality in this data set. And so therefore you can see that by doing this experiment we can get a good estimate of how the hemodynamics of the pathology that you want to study. And so therefore these type of maps can be very helpful in a clinical setting. So here's an example of CBF maps using the dynamics obtained using dynamic susceptibility contrast of a normal subject without any pathology. You can see the difference in the gray matter and the white matter blood flow can be easily seen, and it's quite consistent across the different slices. And here I would also like to point out that there is very high blood flow or signal in the CBF maps where the arteries are, in this case the middle cerebral artery, and therefore it's actually, you have to, when you look at these maps, you have to be careful that if you are looking for pathologies close to large blood vessels, you have to make sure that you don't miss them. So even though we have a good way to come up with these parameter maps, there are errors in different steps in the calculation of these maps. For example, in the beginning we assumed that the change in the relaxation rate with concentration is linear for arteries and tissue, but it is actually, that assumption may not be strictly correct, and if that's the case, then we will introduce some errors there. And also the arterial input function that we determined is sensitive to partial volume and the vessel orientation effects, and also sometimes the peak of the arterial input function can be truncated. And another problem is that the arterial input function, where we measure the arterial input function, may not be the arterial input function that is strictly applicable to the tissue that we are looking at, because there is some dispersion when the blood moves from one location to another. So the arterial input function at the tissue can be slightly different from where we measure it. And also in the process of deconvolution, there could be errors because that process is sensitive to noise, and also the time at the bolus actually arrives. So therefore, because all these errors, this technique is better suited to for determining relative parameter maps. If you want the absolute CBF or CBF values, then we need to acquire additional data so that we can actually determine the proper scaling factors to correct for the errors, and therefore, and these scaling factors need to be determined separately. So at this point, we will switch over to looking at the arterial spin leveling technique. So in this technique, what we'd like to do is we would like to measure the signal change, or the MRI signal change, due to tagging or labeling of inflowing blood. So what we normally do is to tag or label the blood before it flows into the brain. by tagging or labeling that, I refer to magnetically inverting the blood here. So what we do is to apply a 180-degree pulse to invert the magnetization of blood before it flows into the brain. And therefore, we will, once you tag, we will wait for a while for that blood to flow into the brain, and we can acquire the images. So what we like to do is we like to measure the signal change due to that process. So in order to do that, we need to have a control image where the blood is not tagged. So the images that I acquired without blood tagging they are called the control images. Images acquired with tagging of blood or inversion of blood, proximal blood, is called labeled images. And difference between the signal intensities of these two images is then related to perfusion. So this experiment basically has three stages. One is the initial phase where we label the blood, and this takes about a few milliseconds to several seconds depending on the type of labeling that you choose to do, which we'll get into later. And then we'll have to wait for a certain amount of time for the tagged blood to move into the tissue, and that could be 1 to 2 seconds, and then we can image. And for imaging, we can use any type of imaging sequence. It could be a 2D, 3D, echoplanar, or spiral imaging techniques. And with the TR depends on the choice of your imaging technique. And in this case, something that's different compared to the DSE is that we can use the minimum TE to maximize the signal to noise ratio, because in this case we are interested in measuring the change in the longitudinal magnetization due to the tagging of blood. So we are not interested in T2 star weighting or T1 weighting, and therefore we can actually use the minimum TE. And the total experiment time in these experiments is about 4 to 5 minutes, depending on the resolution of the images. So here's an example of ASL images. In the top left, you see a control image. This is an echoplanar image, probably about 3.5 millimeter in plane resolution. And so the signal intensity in this image is proportional to, or is the sum of, the signal from the static tissue. This is the static tissue, and the sum of the amount of blood that is present in the tissue. So in this case, since we did not alter the blood magnetization, so we will actually, the signal intensity in the control image represents the sum of the tissue as well as the blood magnetization. And on the bottom, you see the label image, which is very similar to the control image. However, the signal intensity here is now represents the signal from the static tissue minus the signal from the blood, because before acquiring this labeled image, we had previously inverted the blood and allowed that blood to flow into this tissue. So now we have a tissue signal, signal intensity that is tissue signal minus the blood signal. So therefore, when we subtract these two images, we can isolate the signal from the tagged blood that actually flowed into this slice. And subtracting one pair of these images, we get this noisy image. But we can sort of see that we have high signal in the gray matter and the low signal in the white matter. And this is noisy because the signal amount of blood that actually came into this slice is quite small, and that magnetization is quite small. The signal from that blood is quite small. So in order to improve the signal to noise ratio, we can actually repeat the controlled and labeled images multiple times and average them. And here's an example of averaging 24 pairs by taking about 4 minutes. So the signal change that we see, that these kinds of these are called difference images, delta M images, and the signal change that we generally get in this experiment is about 1% in the gray matter, and it's about 2% in the white matter. Okay, so now let's look at the different ways of how to tag the blood signal. Depending on blood magnetization, depending on the strategy that you use to tag or label the blood, we call those experiments as pulsed ASL or continuous ASL experiments. So in the pulse ASL type of experiments, what we do is to invert a large slab of tissue along with the blood below the brain and let the blood that actually got inverted because of this inversion pulse move into the brain tissue before we start imaging. So in the pulse ASL technique, we actually employ a wide labeling slab proximal to the brain, and this slab is created by a very short 180-degree pulse requiring in a few milliseconds. So whereas in continuous ASL case, what we do is to apply a radio frequency and a gradient pulse in such a way to define a very narrow labeling plane. And so if you have the radio frequency RF pulse strength as well as the gradient properly adjusted, all the blood that is crossing this narrow labeling plane will be inverted. So therefore, in continuous ASL case, we define a narrow labeling plane as opposed to a wide labeling plane in the pulse ASL, and we keep that labeling plane on for a longer duration, for about a second and a half or 2 seconds, so that we have enough blood crossing this plane. So ultimately, we will be able to see a significant signal change with enough signal to noise ratio. So the difference between the pulsed ASL and continuous ASL, here we have a wide labeling slab. In the continuous ASL, we have a narrow labeling slab, which is kept on for a longer duration. Okay, so now we know how to create tagged blood and determine the signal change due to inversion of proximal blood magnetization. Now we have to figure out how to quantify the CBF from that information. And so in this case, in ASL, it turns out we can directly use a formula like this to quantify the signal changes into CBF. And the actual formula is slightly different depending on whether you are doing a pulsed ASL experiment or a continuous ASL experiment. But so here what we have is a delta S, is a signal change between the control and the label images, and that different signal is normalized by the equilibrium signal and is scaled by this factor on the left hand side. And this scaling factor depends on multiple parameters, such as the relaxation rate of arterial blood, the labeling efficiency, the labeling time, and most of all these parameters can be determined ahead of time. So this is a scaling factor we generally use as constant from one study to the next. So the parameter that is likely to change from one subject to another is this labeling efficiency, which is which quantifies how well we are inverting the blood signal. If we invert the blood signal exactly 180 degrees, alpha is 1, and if we don't invert the blood 180 degrees, and if it is less than 180 degrees, the labeling efficiency will be less than 1. So in pulse ASL techniques, the labeling efficiency is very close to 1, it's about 0.99. And for continuous ASL, the labeling efficiency is slightly lower, maybe about 0.85 to 0.9. So if we do not measure the labeling efficiency for every study that we do, there will be a little bit of an error due in the CBF that we quantify because of some subject to subject, this labeling efficiency may be different. So now let's look at the actual pulse sequence that we used in the two experiments. Here's a pulse labeling pulse sequence. So in this case, as I mentioned before, the idea is to apply a wide labeling slab below the brain, and here I have sort of have the brain sideways. So on the left, we see the apply a labeling inversion slab uh, to a region below the brain. So when we after we apply the gradient RF pulse and the gradient properly, so we have the blood magnetization inverted within that slab. So these white arrows represents the magnetization of blood after the inversion RF pulse. So after that inversion, this blood will flow in towards the brain, and so therefore these white arrows will move to the right. And at some point, we will then apply a second RF pulse into the same region that we applied the inversion pulse previously. The idea here is to actually define a well-defined bolus of inverted blood in a certain region. So when we apply a saturation pulse to this gray area, we will leave this particular region unaffected, but within that region we know all the blood has been inverted. So during the subsequent period, this inverted blood will move into the tissue and will move into the tissue, and then we will at that point actually acquire the images. So this bar on the bottom actually shows the status of the blood that arrives in a voxel during the pulse sequence. So we can see that at the beginning of the experiment, even though we are tagging, we start the experiment by tagging, the actual blood that arrives at the voxel has been still being unaffected because the tagged blood has not reached the voxel yet. So it takes a while for the tagged blood to reach the brain tissue, and after a while the tagged blood will start to reach the brain tissue and perfuse the brain tissue with inverted blood. So by the time we image, it is possible that because we have created a well-defined bolus of inverted blood, some of the saturated blood will arrive at the tissue. So now in this case, we also, that is the labeled condition. Now in this case, we have to have a control condition. So the control condition is obtained by doing exactly the same thing by turning the gradient off during the inversion pulse. So during this case, there will be no inversion of the blood within this within this white slab, and so the white arrows will be pointing upwards. And so the rest of the experiment remains the same, and we see in this case the control condition, we actually leave the blood that flows into the tissue unaffected. So if you look at the status of the blood arriving at the voxel in the control condition, we see throughout the whole experiment, the blood that arrives at the voxel has longitudinal magnetization along the z-axis. So by subtracting the two images from the label and the control images, we can isolate the effect due to the blood that arrived at the voxel, inverted blood that arrived at the voxel. So here's an example of data that can be obtained with pulse labeling. And on the top, you see a series of control images, and the bottom is the series of same slices, the difference images, that's the control minus label images. And as you can see the good definition of the white matter signal intensity is quite high compared to, the gray matter signal intensity is quite high compared to the white matter, representing higher blood flow in the gray matter. So the advantage of this pulse ASL technique its high tagging efficiency, leading to good signal changes, and also ease of implementation, because this is a simple pulse sequence that can be run on the scanner. It does not require anything extra hardware, as you will see later in the next experiment. But the disadvantage here is the limited coverage of the brain. If you want to cover the whole brain, it is difficult to cover the whole brain without sacrificing a lot of signal intensity. So therefore, the pulse ASL technique is used only in limited circumstances. So let's look at the continuous label technique now. In this case, what we do is to apply a radio frequency pulse, a continuous RF pulse for a certain duration, while a gradient on. Here the idea is to create a narrow tagging plane like this orange line, narrow tagging plane, and this tagging plane, location of the tagging plane is determined by the frequency of the RF pulse and the strength of the gradient. So we make sure that combination is such that the tagging plane is positioned around the neck area, in the neck area. So in this case, what happens is when the blood crosses this tagging plane, it gets inverted by a process called flow-driven adiabatic fast passage. We will not get into that, but the idea is to, when the tagging plane is active, so all the blood that crosses this plane will be inverted. So here's an example. At the beginning of the experiment, blood on both sides of the tagging plane has the magnetization along the z-axis, has not been affected at all because we just started the experiment. After a little while, we see that some of the blood has crossed over, and therefore we see that magnetization of that blood has been inverted, while the magnetization of blood that never crossed that plane is still along the z-axis. And so if you have, when the experiment is, if you keep the tagging on for a longer period, we can have all the blood to the right of this tagging plane inverted. So at this point, we actually turn off the gradient and the labeling and let the inverted blood flow into the tissue. So here's a situation where all the inverted blood has arrived at the tissue, but the blood vessels proximal to that has now been filled with unaffected blood, because during this post-labeling period, there is no tagging at all. So that's the labeling condition. The control condition is to actually turn the radio frequency pulse off and do the same experiment. And because the radio frequency pulse is off in the control condition, there is no so we are not defining a tagging plane. In this case, blood remains unaffected throughout the experiment. So in this case, we have the same situation as the pulse labeling experiment. Here's the status of the blood arriving at the beginning of the experiment is unaffected. After some time, the tagged blood starts to arrive at the voxel in the labeling condition, and in the control condition, all the blood that arrives throughout the experiment has not been affected. So by subtracting the two images, we isolated the effect of inverted blood arriving at the voxel. So this experiment, this continuous ASL experiment, is best performed by using a dedicated coil for tagging. In this case, we actually use a special coil that can be placed on a neck, which is generally referred to as a neck labeling coil. Here's a subject with a neck labeling coil placed in the neck region. So this coil is constructed as two loops, so it sort of wraps around the neck. So when the radio frequency is applied through this coil, we actually localize the radio frequency to the neck region without disturbing the tissue in the brain. So the advantage of this type of experiment is that we can acquire data from the whole brain without any loss in sensitivity. And also this experiment we can produce high labeling efficiency, but the main disadvantage is that it requires special hardware. We have to make these labeling coils because they are not provided by the manufacturer. So here's an example of continuous ASL data that we acquired a long time ago. On the left-hand side, we see the whole the different signal from slices from top of the brain to the bottom. So we can get full brain coverage, and we see the increased signal from the gray matter compared to white matter, and quite homogeneous throughout the brain. And on the extreme right, we see the quantified CBF using the formulas, or slightly different formulas than what I showed earlier, but similar. So this signal intensity in the CBF, these CBF maps, now you can directly measure the CBF in milliliters per minute per gram. So this data was acquired using a 3D experiment. It's a fast pinnacle spiral imaging sequence, and these were quite low resolution images because these were acquired with the standard head coil. These were standard X coil before the array coils were available, and this data needed about 6.5 minutes to acquire. Here's an example of, again, continuous ASL data acquired with a 8-channel receiver coil, but a little bit higher resolution. And the imaging sequence here was a 2D echoplanar images rather than a 3D EPI, 3D spiral imaging sequence in the previous slide. So here again we see a good definition between gray and white matter blood flow, and you could see that the images can be acquired in any orientation. Here's the axial images on the left, and on the right you see the coronal images, and of course these have to be done as separate experiments, and each one of these data sets took about 4.5 minutes at 3 Tesla. So here's an example of a continuous ASL experiment and a patient that had a tumor, and you could see the periphery of the tumor. We have very high blood flow, and the center of the tumor, where it's very low signal intensity, represents that there is no blood flow in the center of the tumor. And we can also see the tumor blood flow is much higher than compared to the normal gray matter blood flow. These are coronal images, and here's a axial image through the same tumor. We can see the low blood flow in the center as well as the high blood flow in the periphery. On the bottom here we have the matching slices. This image on the bottom is a post-contrast T1 weighted image, and it shows the signal enhancement of the whole tumor because now the contrast agent has leaked into the center of the tumor as well. So here we cannot distinguish the high blood flow periphery from the necrotic core in the middle, whereas that is clearly depicted in the perfusion image. And this patient also had some tumors in the below the cerebellum, and we were able to see that. Here we were able to see that because the labeling occurred way down in the neck, around this level. And so therefore we were able to tag the blood that perfused these tumors as well. If you were using some other technique, it is possible that this area would be obscured and we will not be able to see these tumors. So by tagging around the neck region quite low below the brain can sometimes be advantageous. This technique can be done at the 7 Tesla as well. All the data that I showed earlier, they were all acquired at 3T. We have made a surface neck labeling coil for the 7T, and also we used a 8-channel array coil. And here's some data from the 7 Tesla. On the top we see some different images. showing very good contrast between the gray and white matter signal. And this resolution is now about 2 millimeter resolution in plane resolution, but it took about 8 minutes. And in the top row of images, we acquired these images by applying the labeling RF at the correct frequency so that we define the labeling plane below the neck. And the bottom set of images we acquired by purposely changing the RF frequency so that it's negative compared to the correct frequency. And here we see no signal at all. So that was the purpose of the experiment, because by offsetting the RF frequency, we expected not to see any signal, and that confirms the fact that the previous images that I'm showing on the top is actually due to blood flow and not due to some artifact. So all the signal here is definitely coming from the tagging of the blood rather than any other effects. So we can actually do these experiments at 7T on multiple subjects and quantify the signal changes and the CBF, and across multiple subjects we see that at 7T we were able to get about 1.5% signal change in the gray matter, which is a little bit more than at 3 Tesla. And the quantified CBF across multiple subjects was about 76 milliliter per minute per gram in the gray matter, and about 27 milliliters per minute per gram in the white matter. Okay, so at this point we are going to switch to a labeling technique called pseudo-continuous labeling. So this is a labeling strategy that has been presented recently, a few years ago, and has become quite popular. So in this case, it is called pseudo-continuous because in this situation we are trying to mimic the continuous ASL experiment. So rather than having a radio frequency pulse constant throughout the labeling period in the continuous, like in the continuous ASL, in pseudo-continuous ASL experiment, we actually have broken that RF pulse into small individual pulses. So instead of one long pulse, we apply a train of small RF pulses for the same amount of time. Idea is to mimic the continuous ASL experiment with a small high intensity RF pulses. So in this experiment, because the RF pulses are separated, we also modulated the gradients accordingly. So ultimately, when the blood is subjected to this train of RF and gradient pulses, it actually gets inverted, similar to the continuous ASL experiment. Here also we actually define a tagging plane below the brain. In this case, with the tagging plane is a little bit wider than the continuous ASL experiment. So all the blood that crosses that tagging plane gets inverted, and at a later time will change the signal intensity in the label images. So the advantage of this technique is that, again, it can provide whole brain coverage with high labeling efficiency, and most of all, it can use standard hardware. It does not need a special neck labeling coil like the experiment I showed earlier, and therefore this method is very popular, and it is the method of choice in ASL imaging these days. The main disadvantage of this experiment, it can be sensitive to off resonance effects, and so I will show some examples of the pseudo-continuous ASL at 3 Tesla, and here's some data acquired in about 5 minutes. 3.5 millimeter resolution is a quite nice signal change in the gray matter compared to white matter throughout the brain. So this type of pseudo-continuous ASL technique is available in all of the scanners in some form or another. So if you like to perform some ASL experiments, I'll be happy to help. So we have also extended this pseudo-continuous ASL technique for 7 Tesla, and at 7 Tesla this was a little bit problematic because of resonance effects. We had to actually acquire some additional calibration data, but when you make the corrections from the calibration data, you could see that we can get quite good perfusion maps throughout the brain. And these images took only about 4 minutes and with about 2.5 millimeter resolution in plane. Okay, so let's switch gears a little bit. I mentioned I will briefly show some examples of functional MRI performed with arterial spin labeling. So here's a functional MRI experiment done during with a motor task, and during that motor task we acquired arterial spin labeling data, and we processed the data to detect changes in blood flow, not BOLD, changes in blood flow during the task. So here we see the areas where the blood flow was increased during the finger movement. We can see the blood flow increases throughout the motor cortex in the cortical regions as well as subcortical and cerebellar regions. And in this experiment we were also able to detect some decreases in blood flow in the contralateral hemisphere. So so in this particular case, I'm showing only the fact that we can isolate the locations of changes in blood flow. In addition to that, when you perform arterial ASL-based functional MRI studies, we can actually quantify the changes in blood flow during the task that you're performing. Here's an example of motor activation, bilateral motor finger tapping. We see the location of the active sites on both hemispheres. So in addition to localizing the active sites due to of the blood flow increases, we can actually quantify the blood flow changes as 78% from these are multiple studies, about 78% change in blood flow compared to the resting state. At a higher resolution, the images on the bottom shows a little bit higher resolution, and here we detected changes in almost 100% changes in blood flow due to the motor activation. So therefore, by finger tapping increases the blood flow to the motor cortex around 70 to 100%, depending on the resolution of the images. So that is something that is different than a BOLD experiment. In BOLD, we can quantify the signal change, but that does not directly relate to a physiological parameter. But here we can get an estimate of the change in a physiological parameter directly, in this case, blood flow. And the same experiment can be used to detect functional connectivity. Here the functional connectivity is based on oscillations in blood flow, not the oscillations in the BOLD signal. On the top you see the functional connectivity maps from an ASL experiment. These are correlation maps from a single subject. That's why the signal intensity is quite SNR is quite low. Here what we have done is to take a seed-based region and correlated the ASL signal across everywhere, all the other slices. We could see the correlations across the contralateral hemisphere across the slices, representing the functional connectivity in the motor area. And here's the corresponding images from BOLD. So in this ASL-based functional connectivity maps, you also have to make sure that it's actually the data are properly high-pass filtered correctly, so that we remove any contamination from the BOLD signal changes. So again, the functional connectivity maps performed with the ASL or perfusion-based experiments allows you to determine the fluctuations of blood flow compared to the resting state. In this case, we measured about 30% changes in blood flow compared to the resting state in the motor area, and the corresponding BOLD signal changes were about 0.3%. So the disadvantage here is these perfusion experiments are less sensitive compared to bold. So therefore, unless you really are interested in quantifying the signal changes, then you're better off actually doing bold rather than perfusion. So here's the last slide. So in addition, so now we have a way to actually measure the functional connectivity maps with bold, and there is functional connectivity maps with perfusion, and this group has actually combined these two pieces of information and created the functional connectivity maps based on CMRO2. So therefore, these maps represents the oscillations of metabolic rate oscillations during resting state. So this is a nice extension of or combination of the two, bold and perfusion, to get at another piece of information representing that is a little bit more localized to the tissue activity. So I think we have covered a lot, and so here's to summarize. We talked about dynamic susceptibility contrast, and we talked about that it is requires external contrast administration, and the acquisition is quite fast. That allows whole brain coverage, but the absolute quantitation is a little bit difficult without extra calibration data. On the other hand, the other technique is ASL. Here, the no contrast is required. Takes acquisition time about 5 minutes and can give whole brain coverage information, and absolute quantitation is possible. We have sequences in all the scanners, and this can be used in the clinical as well as research work. That's all I have. Thank you very much for your attention. If you have any questions, I'll be happy to answer. Okay. Good. Any questions? No? Great. Thank you very much for coming.